Okay, so we watched a video and he talks about making a homemade capacitor, and we're going to do a little bit of reasonable assumption on this. So homemade Leyden jar from film canister. Okay, so let's make some assumptions. I'm going to say that the diameter of the film canister, so diameter is 3 centimeters. So that means that the circumference is going to be 2 times pi times that. So it's going to be 2 times pi times 0.03, so it's going to be 0.188 meters. And so then he made a strip, and let's say, so the strip is going to have a length of 0.188 meters, and let's say the strip is 4 centimeters high, so the area of plate is going to be, I'm going to say up here, height 4 centimeters each. So I'm going to say the area of my plate, or the plate in the video, is somewhere in the neighborhood of 0.00, let's call it 7.5 times 10 to the negative third meters squared. And so I'm going to say the wall of canister is, let's call it 2 millimeters thick. I think that's a reasonable assumption. Yeah, I'd say 2 millimeters thick is a reasonable assumption. So that means that my D is going to be 0.002 meters. So that means that that capacitor has a size of epsilon naught A over D. So it's going to be 8.85 times 10 to the negative 12 Newton meter squared per Coulomb squared. And then the area is going to be 7.5 times 10 to the negative third meters squared. And then it's going to be 2 times 10 to the negative third meters. And so I've got 10 to the negative third meters top and bottom, and so I can go, my C is equal to 8.85 times 7.5. Oh, I'll do it out the way it's supposed to be. 8.85 to the negative 12 times 7.5 divided by 2. We're going to get 3.3 times 10 to the negative 11th farads. And I'm going to write that as 33 times 10 to the negative 12 farads. I'm going to write that as 33 picofarads. So there's a reasonable assumption about the size of that capacitor. Now let's talk about how much charge can he store on that capacitor. So well, here we're going to introduce something that we hadn't really talked about, but But air will break down and conduct electricity Okay, so here's a quick note. Newtons per coulomb or volts per meter are the exact same units, and again we're sort of ignoring units more than we should. But Newtons per coulomb and volts per meter are the same thing. So air will break down and conduct electricity when the electric field is approximately 3 times 10 to the 6 volts per meter. That's just kind of a fact that I know. Now I would say his spark gap was around, I'd say 3 or 4 millimeters. Let's give him the benefit of the doubt, 4 millimeters. So that meant that his voltage that he was putting on was going to be 3 times 10 to the 6 volts per meter and times 4 times 10 to the negative third meters. So I can just do this in my head. It's going to be 12 times 10 to the negative third volts, 10 to the positive third volts. So it's going to be, his voltage was 1.2 times 10 to the fourth volts. That's a reasonable assumption for how much voltage he generated on there. Okay. Then the last thing we're going to do is C equals Q over V. So the Q is going to be C times V. Well, actually, we'll keep going with this, I guess. And so we had 3.3 times 10 to the negative 12 farads. We had 1.2 times 10 to the fourth volts. And so his Q that he was building up was going to be, that's an 11, times 1.2 second EE, about 4 times 10 to the negative 7th coulombs. And then we're going to just divide that by 1.6 times 10 to the negative 19th coulombs per electron. About 2.5 times 10 to the 12th electrons. Okay, so what did he do? He built a little capacitor out of a film canister that had a capacitance of 33 picofarads, and he probably got it up to a voltage of about 1.2 times 10 to the fourth volts by putting a charge of 4 times 10 to the negative 7th coulombs on it, and that's about 2.5 trillion electrons.